my name is Olivier Deheurles. I'm a software developer. I've been working for about 15 years in finance, building real-time trading systems. And about 5 years ago, we got the crazy idea with a few colleagues to kick off a business together. So we founded a company called Adaptive. We are a software consultancy. We build real-time trading systems, and it's been going quite well. So we've been opening 3 offices in the last couple of years. So we have offices in London, Barcelona, Montreal, and New York. And we are now more than 100 people. So today, I'm going to talk about an architecture that we use on several of our projects. So it's kind of weird architecture, probably something you have not come across before. We'll see how we are using techniques generally used in distributed database and how we are transposing those techniques at the service layer level. So we'll give you a quick overview of distributed consensus algorithm. So that's what we use to build cluster services. And then we'll look at some of the benefits we get using this style of architecture. So there we have very much a standard architecture for when we build services. So this is what most services tend to look like. So you have a service, so some code running in the middle server side, and all the data is stored securely in a database. So the database is providing us the durability, and is also giving us a way to change and update the data transactionally. So what happens when we try to make this style of architecture highly available? So basically, we need to double everything. So what we are introducing is multiple services, which basically force us to introduce a layer of load balancing in front of our services. And now our database also need to have multiple instances. And it's doing a lot more for us as well, because now our database needs to be replicating data between multiple nodes. And of course, those servers can fail as well. So the algorithm used there to replicate this data need to be able to cope and to deal with those failures. So the problem we're talking about there with data replication is a problem called distributed consensus problem. And basically, it needs to deal with keep the data consistent across multiple nodes on the database layer, and it also needs to keep the data durable, and even in failure conditions. So even if one of those servers fails, and even if we have a network failure, so network partitions. Fortunately for us, there have been loads of research in that space since the 1970s. So nearly 40 years have been, where loads of people have looked at the problem. So I've picked a few important names there that maybe you have come across or not. So the first one on the left is Barbara Lifskov. She's a professor at MIT. And she's, to my knowledge, the first one to have published a paper describing an algorithm to solve the distributed consensus problem. So her algorithm is called view stamp replication. And she actually got a Turing Award for this work and lots of other work she has been doing. So for those who don't know, Turing Award, it's one person every year for all fields of computer science research. And there is only one person getting that. So she's been doing pretty good work. The second one on the list is Leslie Lamport. So he's probably the most well-known in that space. He's published a very large number of papers and is referenced all over the place. He came up with an algorithm called Paxos, which is used and implemented in quite a few places. And he also got a Turing Award. So you see, this problem of distributed consensus is a very complex one. There have been loads of research in it, and 2 people got a Turing Award for some of the work they've been doing in that space. And more recently, Diego Ongaro, he was a student at Stanford in California. And he was actually studying the work of those 2 and several other papers. And he came to the resolution that actually their algorithms are formally proven, but they are still very difficult to understand and actually very hard to implement. So what he did for his PhD is basically, let's try to find, could we come up with an algorithm which would be actually simpler to describe, simpler to understand, and simpler to implement. And so he published in 2013 a paper called Describing the Raft Algorithm that we will be talking about today. So few implementation using those different algorithms. So Paxos is probably the most well-known and widespread. So Google has been using internally Paxos in quite a few of their systems. So for instance, Google Chubby, it's a distributed lock management system which is used within their distributed infrastructure, use Paxos. Spanner, it's a distributed database which offered ACID properties, is also using Paxos. AWS, so Amazon Web Services, have published a number of papers on their the primitives they use internally in AWS, and they talk how they are using Paxos. And we have Mesos, which is a competitor to Kubernetes, Neo4j. Those systems also use Paxos. Interestingly enough, ViewStamp replication, which was published first, and it's actually simpler to understand and to read than Paxos, did not have any implementation, so was far less successful. I've not come across like commercial or professional implementation of ViewStamp replication. Some of you might have come across Zookeeper. So Zookeeper is like a distributed caching solution where you can store your configuration, and it can also help you when you have a distributed system to do coordination. Use its own consensus algorithm called ZAB, and we have Raft, which I was talking about just before, is a bit more recent and is used by etcd and Consul, which are similar to Zookeeper. So let's talk about, I'm going to give you an overview of consensus algorithm, see what it looks like, and I'm going to use Raft, to describe Raft. So what it is, it's basically Raft describes a protocol of interaction between multiple nodes. So what we are trying to do is, we have a cluster of servers, and we are trying to have those servers agree on the overall state of the system. And Raft describes how those nodes are going to communicate and the algorithm you have running on each node to achieve that. So the first thing to notice is that you can't solve the distributed consensus problem with only 2 nodes. Because what happens if you get a network partition between those 2 nodes? Those 2 nodes can't communicate anymore. So basically, they don't know what's going on the other side of the partition. So either they both stay active, and what would happen, their state would diverge, and they are not consistent anymore, so that doesn't work. So basically, a 2-node cluster, you can't make that work. You need a minimum of 3 nodes. So typically for those type of clusters, they come in 2 shapes, either with 3 nodes or 5 nodes. So 3 nodes is going to, to give you the flexibility of having 1 node failing. You always need to have a majority of nodes available for the system, for the overall cluster to be active and able to process client requests. With a 5-node cluster, you can lose 2 nodes. So, and it's important to remember that it's about being able to have nodes failing, but also network failing. So same case, if the network fails, with a 3-node cluster, we are able to have 1 node partitioned. The 2 others need to be able to talk together. Otherwise, the whole cluster is no longer responsive. And with a 5-node cluster, you can have a partition and have 2 nodes out of the cluster. So the first step of Raft is actually to nominate a leader within the cluster. So the Raft protocol describes how those nodes are going to communicate. I'm not going to go into details there, but basically what is important to understand is that for the cluster to work, you need to have one of the node elected leader, and all clients are going to be connecting to the leader. So how it works? Clients would have, in their configuration, they would know the IP address of all the different nodes of the cluster, and they're randomly going to connect to one. If that node is a follower, it will just redirect them. So tell them, no, I'm not the leader, talk to this other guy, and they all end up connecting to the leader. so that's the first step, basically getting the leader elected and getting clients connected to it. Once you have that, clients can start sending requests to the cluster. So that's what I'm showing there with the red square. So we have one client sending a message to the leader, and we're going to see what happens to get this information replicated across the cluster. So the first step is the leader is going to sequence all those messages. So it's getting requests from multiple clients. It's going to build a single sequence and apply a sequence number to every single message, one after each other. And what it's doing at the same time, it's storing this message in a log on disk, because we want this system to be durable. If we shut down the overall thing, we want to keep that state. So we need to be able to recover from a complete failure of the cluster. The next step is basically to replicate that message. So message 1 is going to be broadcasted to all the followers, in this case, 2 other followers. The followers are doing the same. They are going to apply the message to their respective log at the same sequence number, acknowledge back to the leader. And once that's done, so as soon as the leader have seen that a majority of nodes in the cluster have seen that message and acknowledged it. So in the case of 3-node cluster, we need 2 nodes, so including the leader, to have seen the message. The message is marked committed. So the message is basically ready to be processed. We are happy. We know that this message has been seen by a majority of nodes. And the next step is basically the leader is going to say, yeah, this message is committed. You can also mark it as committed in your log. And the process carries on like that. So for every single message coming in, we've got sequencing happening. So the leader is sequencing the message, replicating them, and then marking them committed. So overall, what is important to understand is that the leader is building one sequence of truth, of committed messages, and what the algorithm gives us is a guarantee that this sequence is going to be exactly the same for all the nodes in the cluster. So the followers will see the same sequence of committed message, and this guarantee holds even if we have a node failing or if we have network partitions. And what you can note as well at the same time here is that this architecture is quite close to the concept of event sourcing. So the log I was talking about, where we persist all those messages one by one, we will see how we can use it to basically recover the system. So in event sourcing, it's slightly different. In CQRS, you have basically write models which receive commands and emit events, and we are sourcing those events. In this approach, we are directly sourcing the commands. So we keep a log of the commands. So that's why I'm talking about command sourcing here. OK, so basically at this stage, we have managed to replicate this sequence of incoming message, but we still haven't done anything with them. So the next step basically is going to process, do something with that message. What we need to do there in this specific architecture is we need to make sure that the logic which is going to run within our cluster is deterministic. So because each node is going to receive exactly the same sequence, we need to make sure that each node is doing exactly the same thing. So internally, if we zoom into a node, like there I'm showing the leader, but it's exactly the same on the other nodes. You have basically 2 modules running. One is called consensus module, so it's the implementation of Raft. So it's what is implementing the leader election, the log replication, and this archiving of message. And once we have a committed message, the consensus module is going to dispatch that message into what is called the state machine. And the state machine is where you are actually hosting your code, your logic. So if you're implemented a distributed cache, this is where you would put your code to manage client requests for your specific problem. Yeah. So in terms of deterministic execution, there are a few things that we need to manage specifically in this kind of system. So time is one. So we can't have each node using the system time, because when you're in the distributed system, the clock on your different servers is going to drift slightly, and those different nodes are going to see different time. So what you do instead is time gets injected into the system. So it's a bit like the same concept as inversion of controls. It's don't call me, I will call you. So you get something external to the cluster, sending message to the server, and all those messages, while they are sequenced, they get timestamped. The timestamp is becomes part of the message. It's like a header on the message and gets replicated to the other nodes. When each node is processing the message, they are looking at this time, the timestamp, not the current system time. And there are a few other things you need to be careful with, like random numbers. Clearly, that's not deterministic, but you can generate deterministically a sequence of random numbers if you take a random number generator and seed it with the same thing. So that's what you would do. You would instantiate on each node a random number generator and seed them with exactly the same thing on all the nodes. And after that, when you get random numbers, you're guaranteed that you will get the same sequence. So let's have a look at a quick example. So I'm going to show you some simple code to see how we can put that into action. So what we are going to do there is implement a distributed hash map. So the first thing to do is we're going to define the protocol. So how our clients are going to interact with this distributed cache. So we have a put request, which takes a key and a value. So that's to write something in the cache. And in response, we get just an acknowledgement telling us if it was successful or not. And then we have a pair of messages for read. So a get request at a key, which returns us a value. The logical view you have on the right, so basically what you see there is you have requests coming in, then being processed by the consensus module, which is doing like sequencing the replication. And once message is committed, this message is dispatched to the state machine. In the state machine, I have two very simple classes. One is a message handler. It's going to take that message and actually call on our clean internal model, which in that case is called key value store. So if we look at the code, this is what it looks like. So we have on the left the message handler, so which is basically so we have the accept method, which is being called with our message. We are basically switching on the type of the request, casting the request, and then calling a method on the store. So on the left, we are dealing with messages. On the right, we just have simple, plain old Java object, like a basically where we can do a clean modeling of our specific domain problem. So in that case, we're just basically wrapping a hash map. So if you pick a Raft implementation, like there are many open source implementation, and you stick basically that much code into it, you transform what is a hash map into a distributed hash map. And you have basically a distributed cache, which is fault tolerant. So it's pretty powerful stuff, and you see the effort is not massive to get there. So basically, the thing is, what is quite surprising is that people have been using this approach and those technology to actually build very like low-level infrastructure stuff, like you see distributed log systems, database, distributed cache. But actually, you can basically put any logic in there in the state machine. And that's what we've been doing on several of our projects. So basically, we are taking this infrastructure and putting in the state machine our application logic, our service logic. So this is basically what the system looks like. So you have clients at the top, which could be like UIs or other services, and they're talking directly with this cluster, and we have our service logic, which resides in each node in the cluster. So now what we're going to look at is what are the benefits. So now that we have tried this thing on several projects, can give you some ideas of the benefits we have seen of going and trying such architecture. The first one comes to the way Raft is designed. So you have on one side this consensus module and the other side the state machine. There is actually a very clean separation of concerns between them and a very thin interface. So on one side, you have the infrastructure, so the Raft infrastructure, which is doing loads of stuff for you. So it's basically taking care of high availability, so making those nodes fault tolerant. Also there is a lot of work you have to do in the infrastructure to make this stuff very fast. So in finance, we have implementation of that, which are running hundreds of thousands or even millions of messages per second. So you can make this stuff go very, very fast. In terms of, it's also looking after the durability for you, because we were talking about the RAF log. This log is persisted on all servers, so we get durability from this infrastructure. And it's also managing messaging for us. So all the inter-node communication within the cluster is going to be managed by this infrastructure. And depending on the implementation you are using, sometimes it's going to give you as well the messaging part to have clients communicate with the cluster. So I've put one example there called Copycat, which is a very good open source implementation, well documented. So I would suggest for you to have a look if you're interested. And basically, once you build your system on top of this infrastructure, your state machine code actually can be very simple, because there is you don't have any dependency in your code on the infrastructure. The infrastructure is calling you, so it means you don't have dependencies on frameworks or libraries. So you can really focus on just your domain, your problem, and come up with a clean design for that. Another aspect that you get with this architecture is, because you have the guarantee that the state is going to be consistent between the nodes, and that's a given with the consensus algorithm in place, basically you can be quite aggressive in terms of data that you are going to keep warm in the cluster. What I mean by that? So when we looked at the initial architecture, our service layer was stateless. Each time we receive a request, we need to go to the database to get the state we need, bring it back in the service layer, and do our processing. There, we can change completely the model. So this model is very stateful. We can basically bring inside the cluster and give the cluster the responsibility of a big part of the state we are managing. And what it means is, when we get a request, we tend to have all the data we need already warm in memory. So it's just basically synchronously traversing a graph of objects, running the algorithm you need to do, and reply. And one side effect of that, having this locality between your logic and your data, means that those systems can go really, really fast. So the state machine tends to run, because it needs to be deterministic, then generally the business logic will run only on one thread. And people generally think, one thread, that's not going to go really fast. If you're using one thread and you have your data and your logic in one place, actually it can go very, very fast. No database. So because we have, so this one is a bit like, who would consider building a system without a database? Actually, with this architecture, I'm not saying you don't need a database. Like in the systems we build, we have one, but we decide which piece of data the database is good to deal with, and which piece of data should be basically managed and owned by the cluster. Because if you have data which is going to live at the same time in the database and in the cluster, you have the problem that you need to deal with the consistency of this data, and that's very painful. So it's it's much better when you design your data model to figure out, okay, which part of this graph do I need just at runtime when I'm processing those transactions, and maybe that's better to stay in your cluster. And maybe there is other stuff, data which is going to be like archived. So in our case, in finance, this is going to be trades, for instance. You have like hundreds of thousands or like billions of trades. You don't want to keep all this stuff in memory forever, so you're going to offload that to the database, and database is very good to deal with that. Another mechanism we put in place is called snapshotting. So because this log, if you have a system which is running 24/7 and is going to run for months, the log can become absolutely huge. So it would become a problem if you fail and you have to restart a node, and to bring it back in the same state, you need to replay this whole massive log. That would take quite some time. So the mechanism of snapshotting is basically, you are going to look in the state machine at all the state you have, and you are going to flush that to disk. And you do that at a given sequence number within your raft log. So next time, if you restart this node, what you will do is you grab the last snapshot, It's a given sequence number, and after that you're going to replay all the message after that. And because the logic is deterministic in your state machine, you will get back exactly in the same state. Another interesting aspect with the architecture is the experience you get when you encounter fault or problems in production. So what does it look like with most systems today? Basically, you have an exception blowing up. You're going to try to grab the logs, start going through. Maybe it's multi-threaded code, so you have like log statements interleaved all over the place. And after 15 minutes going through all this stuff, you realize that you can't make sense of it. You have some log statements missing. You don't have enough information. What you do with those systems is very different. You don't use, you can have application logs, but the first thing you're going to use is actually the raft log. So what you would do is, if you have a test environment where something blows up, you connect on the server, grab the raft log, load it on your workstation, load your ID with the same version of the code, and you replay the log. Because your code is deterministic, the same exception is going to happen at the same place. And that's super powerful. And that works with exceptions, but that works with anything. There is something you don't understand, given behavior, you can basically replay this log as many times as you want with a breakpoint and see what's going on. So that's for debuggability. Your application log as well, because your state machine runs on a single thread, your application log tend to be very readable. Basically, what it would look like, it's, I received this message, this is what I've done when I process that message, next message, this is what I've done. So it's all sequential, very easy to read. So an obvious benefit is basically this resilience you get out of the box. You don't have in your application logic to think or to write code about how am I going to make this system highly available or fault tolerant, because this is what Raft gives you out of the box. And that, again, is something which yields to much more simple business logic and much more simple application logic. So I mentioned it before. I think this style of architecture is really a great environment, basically to reason properly about your specific business problem. Your code is not polluted by frameworks and loads of libraries in the state machine. Basically, you can. What we are using is just plain old Java objects, data structures, algorithm. There is nothing else in there, and we don't actually, on our projects, use any library in the state machine. We just need Java. So. Another aspect that you can get with this architecture, so the way Raft is described is very much like request response, but actually you can change slightly the implementation to get an event-driven system. So basically, what I'm showing there is just an example. So we have client 1 sending a message to the leader. The leader is going to replicate that message to followers and then dispatch that message to the state machine. If we have connectivity between the clients and the leader using something else than HTTP, so using a duplex communication channel like TCP or WebSockets or something like that, basically we are capable from the leader to be pushing stuff back to clients. So we receive a message from a client, and we react to that by dispatching messages to other clients. So we can implement other flows than just the pretty boring and dumb request response. Okay, so I'm going to wrap up. As I said, we are using this architecture in finance, but to be fair, I think this can work. It's quite widely applicable. I think it can work for lots of problems, and I think it deserves a bit more attention. I'm quite surprised that this architecture is not more talked about. So if you want more information about that, maybe you've heard about the LMAX architecture. So a few years ago, they were talking about the disruptor and all this stuff. So LMAX runs with a very similar architecture to that. They don't use Raft, but the overall approach is similar. The Raft paper, you should read it. It's just a few pages. It's very approachable. I've written as well a few weeks ago a white paper which is along the lines of this talk, so you can have a look at that. But I think the best way to learn about this stuff would be to actually come and work with us. So we are hiring quite a few people at the moment. We have an office in Barcelona, so if you guys are interested, come and have a chat. So there you have the URLs and the email. We have a booth there. Actually, just after the talk, we are going to be offering those headsets. So if you have a ticket, you should come and check if you if you are the one. Okay, thank you very much. Any questions?
I would like to know pros and cons between this solution and event sourcing, for example, because I'm not quite sure how it fits in there.
Yeah, so even sourcing, there are lots of similarities, but basically even sourcing is not something which is going to give you a consistent state between your servers. So when you are basically, the thing is there are different variation and definition of event sourcing. But if you look at CQRS, for instance, when you have your write models are processing incoming requests, what they need to do is go and load data from the event store, replay the event store to get back in the current state, and process that message. Within this architecture, you have the current state of the system in memory. So when you receive the request, you're directly able to deal with it, and you're guaranteed that this state is consistent. So in the CQRS model, you receive the request, go to the store, reload the events, recompute basically this aggregate that you are going to, where you're going to apply some logic on, and you are going to emit a new event. The thing as well at this stage, what can happen is you could have something else, another write model, having written something, another event. So you need basically to go back to the store with like a CAS operation, so a compare and swap. So you need to go back to the store, check that nothing has changed since you read the data. You don't have to do all this dance and all this complexity when you are using this architecture, because all your nodes are processing a sequence of message one by one, and you're guaranteed that when you're processing the message, the state you have in the state machine is completely consistent between the different nodes.
But you could also have that information in using CQRS and event sourcing. You could also have that information in memory. So if you have that information in memory, it's hard to me to see where's the difference. So
what do you mean having the data in memory? Because if in CQRS, in your write model, if you have the data in memory and you have multiple writes model, how do you make sure that those write models are consistent? You can't. Because your different write models, they are going to basically emit events into the store. So if you have two nodes, two write models at the same time, receiving requests from different customers addressing exactly the same entity, and you are going to mutate something on that, basically you have a race condition there. And the only place where you can basically do an arbitrage and decide is at the event store level. Whereas there, the state is consistent. So basically, in the securance sense, you could think that your write model are running within the cluster, and they are guaranteed to have consistent state between them. And I don't think you have this guarantee when you are using CQRS.
Thank you.
Hi, thank you for the talk. What kind of infrastructure typically is required for a systems like that?
You mean hardware or? Yeah. Like we run those systems on premises for some of our clients or on AWS. So we have actually we have some running on Google Cloud as well. But generally, what you would do infrastructure-wise, so if you're using AWS, if you go with a 3-node cluster, you would have one node in different. You would pick a region where you have multiple availability zones, 3 ideally, so you can have your nodes across the availability zone. Sorry. This means that you can lose a server. You can also have network issues, which would your cluster will continue to work as long as you have 2 nodes available. And if AWS lose in that region an availability zone, your cluster is still operating. So that's a pretty good setup. And in terms of like CPU and memory or those kind of specifics, in terms of threads, you need basically, you want to have 1 core available for the state machine thread, plus a few threads depending on your I/O needs, but that very much depends the type of infrastructure you are using, the Raft implementation you are using, but generally something with like 4 or 8 cores. Memory completely depends what you're doing in the state machine. Some of our systems have a very small heap, like it's going to run with like 25 meg. Some others, you need several gigabytes. And in terms of disk, you tend to want like SSDs, fast disk, because you are writing to this event log, to the Raft log. So you want disks which are able to keep up. Or it can become the bottleneck of the overall cluster, basically. Does it answer your question?
Pretty much.
Okay.
Yeah.
Hello, thanks for the presentation. Since you stated in your some slides, you always have to connect to the leader, but this seems like a bit of bottleneck. Do you think it makes sense to also connect to the followers for only read replicas or something like that, since it's also committed information?
Yeah, no, that's a very good point. So generally, when a database would tend to do that, so you need to be connected to the leader to have what we call linear readability. So it means if you want to have guaranteed complete order from the client perspective to what is happening in the cluster, you need to be talking to the leader. If you want weaker guarantees, if you are happy to emit a query to the cluster and have the query being served by a follower, it's possible that the state it sends, like the response you get back, is slightly out of date. Sometimes it doesn't matter, sometimes it does, depending on your use case. What we tend to do is go for the simplest approach. Like, as long as your system is not going to have like performance issues by sending everything to the leader, just send everything to the leader. If you see that depending on the scale you have and like the client base you have, yeah, you might want to do that. So have some connections going to followers. So for queries to be served by followers. Not talked about it during the talk, but what needs to go in the Raft log is actually just the commands. So stuff which is going to change state in the state machine. If you're just doing a read, that doesn't really need to be replicated across. That can be served just by one node. But if you want the guarantee that you're getting like consistent state on your query, you need to be issuing that query to the leader, and the leader actually needs to be talking to the other node, because the leader could think he's still a leader, but he's actually no longer a leader. Somebody else has been elected. Yeah, so hopefully that answers.
Also, how is the fact that if you want to shrink or grow your ensemble of nodes to 3 to 5, because with my experience with Zookeeper, for example, it's a bit of a nightmare to try to grow or shrink. How is this in Raft?
So basically, this is covered by Raft, so not in the shorter version of the paper, but if you look at this PhD dissertation, there is a whole section explaining how you are going to dynamically, while the cluster is operating, add nodes or remove nodes from the cluster. So to do those operations, you need to have the cluster fully available. So for instance, you can't, if you have a fault in the system and you have lost 2 nodes and you have only 1, the cluster is no longer available. So you can't change the state of the cluster and add new nodes. So you need to have the cluster formed, and after that you can have basically administration message being sent to the cluster to add a node at runtime or remove one. But to be fair, that's something you would do, like, for instance, if you have 3 nodes, you lose 1, and you're getting worried, and you can't bring that node back, so you need to add another one in place. Growing a cluster from 3 to 5 nodes when you are in production, like adding nodes in this kind of architecture is not going to help with throughput or with performance. It's really about high availability, fault tolerance. So generally, you're going to decide upfront if you're going to go with 3 or with 5, and then you tend to stick with it. And there are, like, again, I did not really have time to cover that, but there are other ways to deal with scalability. You can have part of your state managed by the cluster and have another layer on top of services which themselves are like completely linearly scalable. And basically what generally you would tend to do is the cluster would be responsible of part of your domain, and the other layer is going to be responsible of anything which is user specific. So would load state which is specific to this user I'm currently dealing with. And that stuff can scale very well. We're good? Thank you very much.